Okay, part 2. So I think this actually connected a lot of dots for me because I think this is what we were getting so confused about way back when we first started meeting, actually. So this number 19 and the next couple problems that we're doing, the key difference here is understanding what the difference between a sequence and a series is. A sequence is numbers that just are numbers. And a series is when that sequence gets added up to infinity. That is the key difference. It's whether this is just these numbers or are we adding up these numbers from n equals whatever to infinity. And we'll go through them, obviously. So we're going to go through number 19. So here, let a sub n equal n squared plus 1 over n cubed plus 1. Determine whether the sequence n equals 1 to infinity. So this is this notation. Converges. So this is when we take the limit as n approaches infinity and we see if it converges to a singular number. If it converges to a singular number, then it converges to that number. Right? We're not adding up these numbers. So we'll go through that more when we actually get to the limit one, and we'll kind of talk about those differences there. So all I need to do here is take the limit. Again, this is not a series. Limit test proves convergence not for series, only for sequences. Key difference there. All right. So if I take the limit as n approaches infinity of n squared plus 1 over n cubed plus 1, fastest way is just dividing by the highest power of n in our denominator. Our highest power of n in our denominator is n cubed. N squared divided by n cubed, 2 are going to cancel, so we just have 1 over n plus 1 over n cubed. N cubed divided by n cubed is just going to be n cubed divided by n cubed, or 1, plus 1 divided by n cubed. And here, as we plug in infinity, all of these terms are going to go to 0 because we have 1 over infinity, 1 over infinity, 1 over infinity. So it's going to be 0 over 1 plus 0. So this equals 0. So this converges. The sequence, just the numbers itself, and up approaching 0 as n gets really big. There we go. So now when we move on to your next one, number 22, don't think I'm going to actually erase this because I think it's based off of... No, we'll have to come back to this. Maybe I can jump. Yeah, let's jump. I'm going to jump to number 24 because number 24 is this basically the same problem. Yes, it references a sub n and then says determine whether the series. So now the sum as n approaches infinity of these numbers. So limit test is a good place to start because it tells you if things diverge. But for a series, when we're summing up these guys, it doesn't confirm whether these converge to 0 because there are exceptions, and this is that kind of famous exception. So it is good to do a limit test just because it's a quick, like, does this just go to a number? Because if it goes to a number, then the series would diverge because even if this, let's say that this approached 1 instead of 0, if we add up 1 over and over and over and over again, that is infinity because we keep increasing it by 1 each time. But here we need to do another test to basically prove that this converges. We know it most likely may converge, but we don't know that for sure. So this we can do, I think a comparison test would be our best one because we can compare this to p-series. So I can compare to whenever we compare to something, we normally just drop our ones or whatever numbers that we have floating around because they are kind of inconsequential when we plug in infinity. So I can compare this to n equals 1 to infinity of n squared over n cubed. This would end up simplifying to 1 over n if we canceled two n's. This is p-series. P-series is when we have a number, just one n in our denominator, and we look at the exponent here. If the exponent is greater than 1, then it converges. If the exponent is 1 or less, then it diverges. There is a proof as to why that is. If you would like, we can go through it, but I'm not going to go through it since we haven't really discussed that. There is a video on it, so you can just like, why does p-series diverge, you know, if you're curious, but it just does. So basically, we know that this diverges. So there are two comparison tests. There is the regular comparison test. I think that was the one that we worked together with the most. And a comparison test is nice because if I can say that this is bigger than this one, then I'm basically done doing all of my work. I don't need to do anything anymore at that point, which is really nice. But since I have +1 and +1 in my numerator and my denominator, it's not really easy for me to be able to tell which one's bigger and which one is smaller. So what we can do is we can do the limit comparison test. And the limit comparison test is when we do the ratio of these two guys. And if the limit of the ratio of these two guys goes to 1, then they either both diverge or converge. And since we know that this one diverges, if we get a limit of 1 as these, the ratio of these, then we know that they both diverge. So I'll take the limit of n approaching infinity of, and it's going to be this guy over that guy. Right? And then I can multiply by my reciprocal. I don't think it matters which one's on top and which one's on the bottom. I'm pretty confident that she did it this way in her solution. I don't think it matters, but I think just do the original divided by whichever one you're comparing it to, because just that's how she did it, but I don't think it matters. So when we multiply fractions, I can just multiply the numerators and the denominators. So this is actually going to be the limit of n cubed plus n over n cubed plus 1. Right? And then we can do something very similar. I can just divide by my highest power of n in my denominator, which still is n cubed. So I'll say 1, because n cubed divided by n cubed, plus 1 over n squared, plus 1 over n cubed. My handwriting is getting funky, but I think you can follow these steps. And then if we plug in infinity, we get 1 plus 0 over 1 plus 0. So this equals 1. So since our limit of the ratio of both of our series equals 1, they both either diverge or converge. And since we compared to something that diverges, then this diverges by the limit comparison test. 2 problems in that one, so not too bad. So we'll do another, because you sent another one. That's like this, with one being the series and one being the sequence, or sequence series. So again, sequence is just a sequence of numbers. Series, adding it up, and that is the key difference here. Oh, okay, so you asked also for number, I just did 19 and 24, so I got to do number 22. D sub n equals 1 plus 1 over 2 to the n. So this, it says, for all of these questions, determine whether the sequence, in this case d sub n, as n equals 1 to infinity. So this is just for our sequence. So here I could just find the limit and say, what is my limit as n approaches infinity of 1 plus 1 over 2n? As I take 2 and have a higher power, a higher power, a higher power, my denominator is going to get bigger and bigger and bigger. And this is actually going to, this portion is going to go to 0. And I just have a 1 still floating around. So this is still going to just be 1 because it's going to end up being 1 plus 0. So this converges to 1. And I'm going to triple check number 22 just to make sure we're on the right track. Yes, the sequence is convergent because it just goes to a number. Nice, easy, lovely. And then when we jump to number 27, determine whether the series of 1 plus 1 over 2 sub n, whether that is convergent. And again, we're adding up these numbers. So here, I can take the limit as n approaches infinity. And here, I need to plug in my computer. In our last example, our limit went to 0, which is what we want, because basically when you're doing an infinite series, you want it not to be adding another number on top of it as n approaches infinity. You basically want to be adding 0 at the tail end, and that's the only way for a series to converge. That's why it's a divergence test, but it's not a convergence confirmer, because p-series is a great example that just because the limit approaches 0 doesn't necessarily mean that the series converges. And I don't have enough brain power currently to fully understand that, but there is a proof of why it works out to be that way. So here is our example where this is a great way to just prove divergence. Here, my limit as n approaches infinity is 1. So as this approaches infinity, I'm going to just get 1 plus 1 plus 1 plus 1 all the way, all the way, all the way to infinity. So if I just keep adding 1 and 1 and 1 and 1 and 1, this is going to diverge, and I actually don't need to do any comparison test, ratio test, root test. I don't need to do any of that because the limit equals 1, and we need the limit as n approaches infinity to equal 0. And again, here is our big difference, why our sequence converges, but the series diverges. Key distinguisher there. Not too bad. Kind of a quick problem, mathematically, which is kind of nice. Let me plug my laptop in because screen went really dark. Okie dokie. All right. So hopefully that tied up all of the loose ends. It certainly did for me. So hopefully it does for you as well. All right. Keep chugging along. Okie dokie. So what was after number 27? Then we have number 30. Determine whether the series is n equals 1 and approaches infinity of 1 over 1 plus 2/3 to the n. Determine if this is convergent or divergent. So we can do the same thing. We can take our limit as n approaches infinity of this guy. And this one's actually not too bad just because we don't really have a whole bunch of junk floating on. We have just a 1 and a 1, and the only piece that we actually need to worry about is what occurs here. So this is just, I think it's called geometric series because geometric series is when we have a fraction raised to the power of n, like say a over b, a fraction. And this approaches 0 if a over b is less than 1. Then this approaches 0. Because if this is less than 1, then when we take it to the power of n, we are going to get smaller and smaller and smaller numbers. I did this as a test, just as a sanity check. You get 2 over 3, because that's to the 1. And then if you square it, it'd be 4 over 9. If you cube it, it would be 8 over 27. That would be 16 over 81. 32 over 243. And we already, at our fifth number, we're already at 32 over 243. Like that got, here it's kind of hard to tell, but here you can very clearly see that 32 is not even a quarter of 243. So it's a remarkably smaller number. And that's only 5 terms in. So just knowing this general rule, and this also helps you prove a certain series at some point. But just knowing that as the limit approaches infinity, that part equals 0. Just that part. So this actually equals 1 over 1 plus 0. 1 over 1 plus 0 is 1 over 1, which is 1 if the limit approaches infinity. And in the example that we just went over, if our limit approaches 1 as n gets big, if this is a series and not a sequence, we are going to be adding 1 over and over and over again, and it's going to increase our number, which makes the series not convergent because it is just going to get bigger and bigger and bigger. So our series would approach infinity as n approaches infinity. Sound good? All right. So keep moving along. What number next? That was number 30. We need to do number 34. Number 34. For what values of x does the series e to the negative n x converge? So this, I think it's just phrased a little bit differently. In all of the problems that we've been working through, it kind of phrased it like find the radius of convergence, which is asking what values of x does it converge, or the interval of convergence, because those are the x values that you could then plug in and figure out if this then converges to a singular number, or if it would shoot off to infinity. So here, for those problems, we always did the ratio test. So I say don't mess with it. It keeps working for me. So whenever I'm looking for values, whenever there's an x in here, I'm just going to do the ratio test. So this is our, I'll write this out, a sub n equals e to the negative n plus x. A sub n plus 1 is going to be e to the negative n plus 1 x. And then we can set this up as a limit as n approaches infinity of n plus 1. So this one, order does matter, over e to the negative n x. All right, and then we'll do a little bit of algebra. So we'll say negative x times n and negative x times 1. So this will be e to the negative x n minus negative x over e to the negative n x. I'll switch these so they're in the same form. We've been doing a lot of algebra with our exponents, so I can split this up. Even though they're minus signs, the rule is the same. So I could say that this is e to the negative n x times e to the negative x over e to the negative n x. Split those up, and then those cancel, which we love. And then I just have, since I don't have an n to go into anything anymore, I could just drop that limit. I don't need to keep writing it. And then I'll have e to the negative x, and I need it to be less than 1. And here, whenever we're solving for these problems, it makes the most sense to write these with real numbers. We don't really like negative exponents. They don't mean much to us. But we know that 1 over e to the x equals e to the negative x, right? So there are certain values for which this is less than 1 and certain values for which this is greater than 1. As of right now, if I plug in a positive number, this is going to be less than 1, right? Yeah, it just can't be. We don't know if it can include. I wonder if she tested 0. Anyway, sorry, I'm getting ahead of myself. So this is going to be, because when x is 1, this is 1 over e. E is like 2.7, so that'd be 1 over 2.7, so that's going to be a fraction. When x is 2, that's going to be 2.7 squared. X is 3, so this number is going to get smaller and smaller and smaller as x gets bigger, but if it is positive, then it is less than 1. So this will be when x is positive, 1 over e to the x is less than 1. And then when x is negative, then if we have e to the negative x in our denominator, then the negative exponent would tell us to put that up into the numerator. So if we have x to the negative 1, that would, or e to the negative 1, that would say that's just e to the 1, or 2.7. so on and so forth. So when x is negative, this would be e to the x is greater than 1, which means that our series would diverge. So now I think we just need to know what it is when x equals 0, because we know what happens when x is positive. We know what happens when x is negative. So now we need to figure out what happens when x equals 0. So then we have, just plug this in. This is what we discussed a couple weeks ago when we said we need to test the bounds. She doesn't do it all the time. I think it just depends. It depends if she asks which values of x does it converge or diverge for. Because at that point, she's asking whether or not to include the numbers like 1 or 0 or stuff like that. If she's just asking for the radius of convergence, it does not appear that we need to test those end values because she doesn't in her solutions, and she's just asking for the radius. She's not asking if that end point of the radius is included or not. So if that makes sense, that may save you a little bit of extra time because this one's not too bad to plug in, but they can be annoying to plug in. So if I just plug in for x equals 0, this is going to be e to the 0, which equals the sum as n approaches infinity of 1. And we know that if we add 1 over and over and over and over again, it approaches infinity. So this diverges. So x can be any positive number. What is the actual question that she asked? For what values of x converge? So x needs to be greater than 0 for convergence. That would be our final answer. So yeah, definitely an interesting one, especially because all of our intervals have been between like 1 and -1, so this one's definitely different. So I think it's just when you have it looking a little bit different, not just x, but you have x as your exponent, then something like this, thinking about it, is going to be required, which is lovely. We love testing our knowledge. But yes, so a little bit different of an answer than what we've seen previously. Okay, so how much time do I have? I'm at 28 minutes, so I'm gonna upload this before doing the next one.